As we move further into trig identities and verifying identities and simplifying trig expressions, first thing I need you to realize is that trigonometry and algebra are not mutually exclusive. Anything that you can do with algebra expressions, you can also do with trig expressions. For example, in algebra we might have x plus 3 times x minus 3. And we know that when we multiply those, we oftentimes will call it FOIL, but we multiply the first terms, the outside terms, the inside terms, the last terms, and when we do that we end up with x squared minus 3x plus 3x minus 9. The middle two terms eliminate each other and we just end up with x squared minus 9. We can do the same thing with 1 plus cosine theta times 1 minus cosine theta. When we multiply the ones, then we end up with a minus cosine theta and a plus cosine theta and a minus cosine squared theta. Two middle terms cancel out. We end up with 1 minus cosine squared of theta. Similarly, if we had sine alpha plus cosine alpha, the quantity squared, well, we would do that just like we would x plus y, the quantity squared. Now you can use the little shortcut trick, or you can just remind yourself that this is x plus y times x plus y. So it's not going to be x squared plus y squared, it's going to have a middle term. Well, when we do this here, sine alpha plus cosine alpha, the quantity squared, we get sine squared alpha plus 2 sine alpha cosine alpha plus cosine squared alpha. And then we can play other tricks with this. For example, we've got sine squared alpha and cosine squared alpha. We know that that's just 1, isn't it? So that gives us 1 plus 2 sine alpha cosine alpha. This is just showing you that even though these are trig expressions, we can treat them like they were variables. This is just a thing plus another thing. Just like x and y are two different things. We don't know what they are. They're just variables. They're placeholders. And so this is the pattern we're trying to show, is that if you have the sum of two things, whether they're trig expressions or variables, you can square them, and this is what happens to it. So moving on now, let's look at our first simplifying. What expression is equivalent to cosecant squared beta times the quantity 1 minus cosine squared beta for all beta on which this expression is defined? Now this is the way your homework states it. They also give you a series of options from which you select. Really low grade homework. I wish I had a way of giving you better identities, but this is what we're going to work with for right now. So we have some squared items, and on the tips sheet that I gave you, it talks about looking for squares. Look for places where you can use your Pythagorean identities. One of our Pythagorean identities is that sine squared beta plus cosine squared beta is 1. Now I'm noticing here I've got a 1 and a cosine squared beta. If I'm living life right, I might be able to turn this equation into one side being 1 minus cosine squared beta, and that will give me a chance to rewrite this as something a little nicer. And we are, because sine squared beta is equal to 1 minus cosine squared beta. So that means in this original expression, I could replace 1 minus cosine squared beta with sine beta, and I won't have changed the meaning of this expression at all. So that gives me cosecant squared times sine squared. Cosecant squared of beta times sine squared of beta. So I've made it look a little nicer. I wonder if there's anything else we can do. One other possibility that we can use when we're trying to simplify things is to write our expressions in terms of sine and cosine. Now cosecant beta can be written as 1 over sine beta. So cosecant squared of beta would be 1 over sine squared beta. And then when we multiply that, we get sine squared beta, or 1 over sine squared beta times sine squared beta. And we know anytime you multiply two reciprocals by each other, you get the number 1. So in this case, cosecant squared times 1 minus cosine squared, all of beta, is equal to 1. Let's try another one. Cosecant squared alpha minus 1 divided by cosine of alpha. Now we just had that sine squared alpha plus cosine squared alpha equals 1, right? And the way we get from one of our Pythagorean identities to the others is by dividing everything by something. In this case, I want a cosecant squared. So if I divide everything by sine squared alpha, we notice that I end up with a 1 plus cotangent squared alpha equals cosecant squared alpha. Once again, I would like to replace this cosecant squared alpha minus 1. So what I'm going to do is play with this equation and see if I can turn it into a cosecant squared alpha minus 1. Gives me cotangent squared alpha equals cosecant squared alpha minus 1. Okay, that'll work. So I can replace this cosecant squared alpha minus 1 with a cotangent squared alpha. So this gives me cotangent squared alpha divided by cosine alpha. Once again, we can use our identities. We can look at this and try to find some way of simplifying it further. If we look at our answers in the multiple choice, we'll see that this isn't one of them. So what is cotangent squared alpha? That would be the same as cosine alpha divided by sine alpha. And again, this is going to be squared. And all of that's being divided by cosine alpha. And just to make this a completely complex fraction, I'm going to say cosine alpha over 1. Because the next trick I'm going to do is invert and multiply. That's how we divide two fractions. So this is going to become cosine squared alpha divided by sine squared alpha, and it's going to be multiplied by 1 over cosine alpha. At this point, we can divide out one of my cosines with one of the cosines in the numerator, and I get cosine alpha over sine squared alpha. I look in my answers, that's still not one of them. So what else could we do? Well, I notice that this is the same as cosine alpha over sine alpha times 1 over sine alpha. Cosine alpha over sine alpha is cotangent alpha, and 1 over sine alpha is cosecant alpha, and this is the answer I'm going to look for in the bottom, and I'll actually find. As a point of fact, these are all equivalent expressions. I mean, that's all we're doing is rewriting an expression the same way or with the same meaning that to look a little differently in order to get something that's easier for us to deal with. Alright, last one. Sine squared theta minus cosine squared theta over sine theta plus cosine theta. Yikes. Let me look at my Pythagorean identity. It was sine squared theta plus cosine squared theta equals 1. All I can do is add things or subtract them from both sides. And I can subtract cosine squared theta from both sides. That gives me sine squared theta is 1 minus cosine squared theta. Or I could say that cosine squared theta is 1 minus sine squared theta. But I can't make this look like sine squared theta minus cosine squared theta. So we need to go another direction. One of the things we want to look for when we're trying to verify identities or simplify trig expressions is to look for opportunities to factor, look for opportunities to get a common denominator, that kind of thing. And in this case, sine squared minus cosine squared, I don't necessarily know if that'll factor, but I do know that if I were to think of it this way, x squared minus y squared, that does factor. That's x plus y times x minus y, right? Difference of two squares. So what I'm going to do is look at this numerator, the sine squared theta minus cosine squared theta, and I'm going to look at the fact that the denominator is sine theta plus cosine theta, and that gives me the idea that maybe I want to factor this into sine theta minus cosine theta times sine theta plus cosine theta. And that's all over sine theta plus cosine theta. I factored it, which this is just like algebra and trig are not mutually exclusive. You're going to use both in both. Well, you don't always use trig in algebra, but you're going to use algebra in trig. At this point, I have a product in the numerator, and I have sine theta plus cosine theta in the denominator. I can divide the top and bottom by sine theta plus cosine theta, leaving a 1 in both places. Sine theta minus cosine theta times 1 is just sine theta minus cosine theta. And it's all over 1 because anything divided by 1 is itself.